Here we're going to look at the notion of a continuous function, or what it means for a function to be continuous at a point A. So I first want to recall the Calculus 1 definition of continuity, which says f is continuous at A if the limit as x approaches a of f of x equals f of a. And in some very special cases, this will be equivalent to our definition, but we don't want it always to be equivalent to our definition. So now here I've got something which is maybe a more proper definition for continuity. And it says a function f from a to r, so a is a subset of the real numbers, is continuous at a in a if for all epsilon bigger than 0, there is a delta bigger than 0, such that if x is in a and x minus a is less than delta, then f of x minus f of a is less than epsilon. And so what makes our proper definition different from our Calculus 1 definition is this fact right here that x needs to be in the set A, and A is like kind of a more arbitrary set. Essentially, when you're working with Calculus 1 type limits, your domain is always like an interval, but this actually sets up cases when maybe your domain has some isolated points. And I want to make that note right here. This definition allows for some weirdness at isolated points A in A. In other words, it seems like you shouldn't have continuity, but you do have continuity at isolated points. So I want to point out that this is maybe something good to look at. Maybe post in the comments some examples you come up with where you have continuity at isolated points, which seems wrong, but follows this definition. And if you're in the class that I'm teaching right now, then this will be one of the group exercises next time in class. Okay, so let's go ahead and look at this theorem, which is some sort of alternative description of continuity. And so it's a three-part thing, and it says the following are equivalent. So the first is that f is continuous at A. The second is essentially the same thing, except instead of these inequalities, like this one right here and this one right here, I've rewritten that as epsilon and delta neighborhoods. So I'll let you guys check that 1 and 2 are equivalent, but essentially what it boils down to is just rewriting these epsilon and delta neighborhoods as inequalities. So it says for all epsilon neighborhoods of f of A, there is a delta bigger than 0 such that if x is in the delta neighborhood centered at A intersected with capital A, then f of x is in the epsilon neighborhood of f of A. So like I said, this is exactly the same as this first condition. We're just exchanging all of these epsilon and delta neighborhoods for their inequalities. Okay, and then maybe the more interesting one, which is the one that we will prove, is that for all sequences x sub n, where those lie completely in our set A, and the limit as n goes to infinity of x of n equals A. So in other words, we've got a sequence which is converging to A. We have the limit as n goes to infinity of f evaluated at this sequence is f of A. So this is sometimes called a sequential continuity description. And this kind of thing is really useful for showing that a function is discontinuous, and we'll use it to show that later in the video. Okay, so let's go ahead and prove this 1 if and only if 3. Like I said before, I'll let you guys fill in the details on part 2. So I want to maybe go ahead and start by assuming that 1 is true. So let's go ahead and suppose 1 is true. In other words, we want to suppose f is continuous at some point A in A. And then we want to start with the hypotheses of 3. And we have any sequence of numbers x sub n from A such that the limit as n goes to infinity of x sub n equals A. And I want to point out that we have assumed 1 is true and the hypothesis of 3 is true, and we want to show that the conclusion of 3 is true. So in other words, we want to show that the limit as n approaches infinity of f of x sub n equals f of a. And we can actually do this super quickly if we recall something that's in a previous video where we look at like the sequential definition of a limit of a function. But we're going to do this kind of from scratch for practice. Okay, so how do we show this? Well, we show this via the epsilon delta definition. So let's go ahead and suppose that epsilon is bigger than 0. I should have said the epsilon in definition. So let's go ahead and suppose that epsilon is bigger than 0. And then let's pick some sort of delta bigger than 0 such that if x minus a is less than delta, then f of x minus f of a is less than epsilon. And I guess I should put out in here that this also has to have the condition that x is in capital A. Okay, good. Now what we want to do is take this delta and use it alongside this convergence right here. So let's do that. So let's go ahead and pick some capital N, which is a natural number, such that if little n is bigger than our capital N, we have absolute value of x sub n minus a is less than delta. So now let's go ahead and talk about why some of this stuff is possible. So we want to be given some epsilon bigger than 0. That's because we want to show this thing in yellow. This is like our challenge. So this delta is picked because we know that f is continuous at a. So this delta comes into existence because of the continuity of f at a. Now this n comes into existence because this limiting value of this sequence x sub n. So those two things are coming into existence for two different reasons. But now we've got x sub n minus a is less than delta. But notice the fact that x sub n minus a is less than delta and x sub n is a subset of a, that tells us that f of x sub n minus f of a is less than epsilon. Great. Where we're essentially just putting this condition on the sequence inside the condition on the continuity of the function. Great. But now if we look at the extreme left-hand side right here, along with this portion, we have exactly built the condition that the limit as n approaches infinity of f of x sub n equals f of a, which is the forwards direction of this proof, 1 if and only if 3 completed. Okay, let's go ahead and look at the reverse direction. Now we're going to look at the reverse direction of this, and we're going to prove this reverse direction via the contrapositive. So in other words, what we will actually prove is not 1 implies not 3. So that would be the contrapositive of the reverse direction. 3 implies 1. But this is a bit tricky because we have to negate the condition of continuity. So let's go ahead and do that. So let's suppose that f is not continuous at a, but we'll use the word discontinuous for that. So discontinuous at a in a. So that means we need to negate this definition over here, but let's recall what that means. That means all 4alls turn into there exists turn into 4alls, and then the conclusions are negated. So this 4all is going to turn into there exists. So there exists some epsilon, I'll call it epsilon naught bigger than 0, such that for all delta bigger than 0, we have, so far I've changed the 4all to there exists and that there exists to a 4all, and now we have to say that x is in a and x minus a is less than delta, but f of x minus f of a is not less than epsilon naught. In other words, it's bigger than or equal to epsilon naught. So we have x is in a and x minus a is less than delta, but f of x minus f of a is bigger than or equal to epsilon naught. So again, this is going to be true for all delta. Okay, so in particular, we want to take a special value of delta, so we know that this kind of thing happens for all delta. So we take a special value of delta and use that in order to construct our sequence, which our sequence will be like a negation of this this third step right here. So let's go ahead and do that. So in particular, if delta n equals 1 over n, there is some xn, which is in A, such that xn minus A is less than 1 over n, so that's my delta n, but the absolute value of f of xn minus f of A is bigger than or equal to epsilon naught. And now we just have to check two things. And I'm not going to check these super carefully because we essentially checked them in a previous video almost exactly. So I'll let you guys check them, and it's a good exercise. So the two things that we want to check are the limit as n goes to infinity of f of x sub n is not equal to f of A. So we can get that just by negating the definition of convergence for a limit, but we see that we have the condition satisfied for that already. That's not too hard to see. So, and the next thing that we need to check is that the limit as n goes to infinity of x sub n equals A. And again, we can do that with an epsilon n argument using the Archimedean principle that for any epsilon we choose, we can find an n such that 1 over n is less than epsilon. So I'll let you guys check that if you need to. But what we have arrived at is a negation of the third statement, and thus finishing this reverse direction of our proof. So we've just proven that 1 if and only if 3. And like I said before, 2 is just a reformulation of 1 in terms of epsilon and delta neighborhoods. Okay, so I'm going to clean this up, and then I want to tie this notion of continuity to a calculus 1 notion of continuity. Now I want to tie together these two notions of continuity, the calculus 1 notion and then our proper definition. And I'm going to via this following theorem. It says that if A is in A and it is a limit point of A, then f is continuous at A if and only if the limit as x approaches A of f of x equals f of A. And so the really important thing here is that we have included this notion of A being a limit point. And that kind of goes along with this weirdness that can occur at isolated points. So let's go ahead and look at the forward direction of this proof. So in other words, we want to suppose that f is continuous at A. So let's do that. So suppose f is continuous at A, and we have xn, which is a subset of A, so this is going to be a sequence, such that two things hold, and those two things are really important. The limit as n approaches infinity of x sub n equals A. So in other words, we've got a sequence that is limiting to A, and the other really important thing here is that xn is not equal to A for all n. So we've got a sequence that is never equal to A, but is limiting to A. And this is something that is not possible if we're at an isolated point, but is possible if we are at a limit point. And that's really important here. Now, the next thing that we want to do is notice by the previous theorem, we have the limit as n approaches infinity of f of x sub n equals f of A. So that's by the previous theorem. And then by a theorem in a previous video, we have this is equal to the limit as x approaches A of f of x. Great. So I'll let you guys look at the proof of this theorem from the previous video, and we just did the proof of this right here. The important thing here is that none of these xn's are equal to A. So, and that's only possible if we are at a limit point and not an isolated point. If we're at an isolated point, well then it may not be possible to find a sequence that converges to A unless every member of that sequence itself is equal to A. Just think about like a singleton that's all by itself. Okay, so anyway, that finishes the this direction. Now we're ready for this reverse direction. So we want to suppose that the limit as x approaches a of f of x equals f of a, and then prove that that means that f is continuous at a, kind of keeping in mind that a is a limit point. So we're going to use this definition of continuity over here, and so that means we need to start with some sort of arbitrary epsilon. So given epsilon bigger than 0, let's go ahead and take delta such that if x minus a is less than delta, then the absolute value of f of x minus f of a is less than epsilon. And so, like I said, this is possible because of this assumption right here. But now notice that this is almost all that we need in order for this proper definition to be satisfied. We also need this if x is an element from A, but that's like easily noted here. So note, because A is a limit point of capital A, we know the delta neighborhood centered at A minus A, in other words, this is maybe sometimes called the deleted delta neighborhood, intersected with A is non-empty. And so since that is non-empty, we can take some x's from there. Those x's will satisfy this inequality, which means plugged into the function f, they'll satisfy that inequality, which is everything that we need in order to finish this like purple underlined part. Okay, I'm going to go ahead and clean this board up, and then we're going to use this theorem to show that a function is discontinuous at a certain point. Now we're going to look at a pretty useful corollary to our previous big theorem. It says that if we've got a function from a to r, and a is a limit point of capital A, then if there exists some sequence x sub n in A such that xn approaches A, in other words, the limit as n goes to infinity of x sub n equals A, but the limit as n goes to infinity of f evaluated x sub n is not equal to f of A, then f is discontinuous at A. This is really great because it gives us a way of showing that a function is discontinuous at a certain point without really like having to negate the definition carefully. All we have to do is find some sequence that approaches some number, but the output of the function at that sequence does not approach the right thing. So the example that I want to give is the floor function, also known as the greatest integer function. So we've got f of x equals floor x. So in other words, this is the greatest integer that is smaller than or equal to x. And our claim is that this thing is discontinuous at all integers. So let's just recall real quick what the graph of this function looks like. So if we've got 1 right here, 2 right here. So between 0 and 1, it is equal to 0 because we can think about this as being like an elevator downstairs. We got to have an open circle there because it's not going to include 1 until you actually hit 1. And when you hit 1, the value will be 1 because 1 is less than or equal to 1. And then here we're going to go up, have an open circle there. Here we'll go up, we'll have an open circle there at 3, and so on and so forth. So this is 2, this is 1. Okay, great. So the thing to notice here is that if you are approaching this number 2 from below, then you will never be equal to the value of the function here. So this is exactly what we'll use. So let's go ahead and take our sequence x sub n to be m minus 1 over n, and this is going to be for all n which are natural numbers. Great. And now it's pretty easy to check here that the limit as n goes to infinity of x sub n equals m. And so maybe how would you do that? Well, you could do that with an epsilon delta proof if you wanted to, or sorry, an epsilon n proof. So maybe let's go ahead and let epsilon bigger than 0, and we'll take a capital N in the natural numbers such that 1 over capital N is less than epsilon. So that's possible, again, by the Archimedean principle. And now what we want to notice is that we have x sub n minus m is going to be equal to m minus 1 over n minus m. Great. but then that is going to be equal to 1 over n, but then that's going to be less than 1 over capital N, which is less than epsilon, and that's going to be true for all n bigger than or equal to n, which is exactly what we need in order to show that this limit is m. Okay, so good. We finished this little proof here that this thing approaches m. Now the next thing that I want to notice is that x sub n is less than m for all natural numbers n. Great. And maybe another thing to notice is that it's always bigger than or equal to m minus 1. So if n equals 1, then it's going to be equal to m minus 1, but then it'll be like in the middle otherwise. But this inequality right here tells us that if we evaluate f at x sub n, we're going to get m minus 1. And that's going to be true for all natural numbers n. Great. But if this is a constant function at all of the values of this sequence, then that very quickly tells us that the limit as n approaches infinity of f of x sub n is equal to m minus 1. Great. But now m minus 1 is not equal to m, which is equal to the value f evaluated at m. So here, notice what we've got going on here. We have a sequence approaching m. So notice x sub n is approaching m. But when plugged into the function, the limit of the functional sequence does not equal the functional value. So we've got m minus 1 and we've got m on the other side. So what this tells us is that f is discontinuous at m. Okay, good. And that's a good place to stop.